While chiral catalysis remains a challenge for chemistry, in biology, enzymes have been catalyzing the reaction with only one enantiomer of a substrate for very many millions of years. Here we see the enzyme phenylalanine hydroxylase, which is involved in the metabolism of the amino acid phenylalanine. It recognizes only L-phenylalanine, and absence or defects in this enzyme result in the disease phenylketonuria. The enzyme is around 300 amino acids in length and shown here in sticks with the hydrogens omitted. So let's have a look at the active site where catalysis occurs and see if we can see how the enzyme recognizes only L-phenylalanine and not D-phenylalanine. Here's the active site with L-phenylalanine shown with the hydrogens present on the substrate, and you can see the chiral center of the substrate is highlighted there. Substrate forms two hydrogen bonds from its amino group to carbonyl oxygens in the protein, and it forms an interaction from its charged carboxylic acid group to the positively charged end of a lysine side chain. What would happen if instead of L-phenylalanine we modelled D-phenylalanine into this active site? Well, there's D-phenylalanine hypothetically modelled in, and we can see that while the interaction between the carboxylic acid group and the lysine side chain is probably still okay, the hydrogen bonds formed between these carbonyl oxygens and the amino group has now disappeared. That interaction cannot take place because the opposite chirality of phenylalanine puts the amide group over on the other side. And over on the other side where that amide group is, you can see that now it is pushing against this phenyl ring in the protein, probably clashing sterically, but this is also an unfavourable interaction. So it's highly likely that D-phenylalanine doesn't fit in the active site of the enzyme because the interactions that keep it there are not favourable.